Rayleigh criterion. Rayleigh criterion specifies the minimum separation between two light sources that may be resolved into distinct objects. Let's take a look at what it means. So in this case, the two light sources are not being resolved, and therefore it did not meet the Rayleigh criterion. This is the case whereby it begins to meet the Rayleigh criterion because the first minima coincide with the central maximum. So we can clearly see that the two central maximum are separated. Hence, this barely meets the Rayleigh criterion. And as far as this is concerned, this meets the Rayleigh criterion. So the Rayleigh criterion is based on the single slit diffraction, where we examine when the first minima occurs. So in this case, sine theta is equal to lambda over A. And A is the slit width, which in this case could actually be the width of an aperture or the width of the telescope. And given that theta is small, so theta minimum is approximated as, given that theta is small, so sine theta is approximated as theta. So theta minimum is approximated as lambda over A. So once we calculated theta minimum as lambda over A, we will actually have the value here. So in order for the light sources to be resolvable, the angular separation between them, which we normally call it alpha, must be larger than theta. So there are specifically two types of questions. So let us take a look at the first type of question. In the first type of question, we typically compare the angle alpha, which is the angular separation between the two light sources, versus that of theta. Theta is calculated based on the Rayleigh criterion, or otherwise it is angle based on the first minima of the diffraction pattern based on the single slit. So using the single slit diffraction formula, sine theta is approximated as theta because we assume theta to be small. So theta in this case is this, and from the theta itself, we can determine the first minima. So in these questions, we can see that so for the source L1, it is based, the intensity of the diffraction pattern is based on this graph that is drawn, and certainly this is the position of the first minima. And when we now take a look at L2, based on the angular separation of alpha, if alpha is exactly equal to theta, then that is when the intensity of the central maximum coincide with the first minima of source L1. So this is actually so in short, when angle alpha is equal to theta, it barely just meets the Rayleigh criterion, which means that the two light sources can be clearly resolved when angle alpha is larger than your theta. So to summarize it, in order for Rayleigh criterion to be met, the answer must be option 2, where angle alpha is greater than or equal to theta. Finally, we look at the last part of the question as to how we can improve the resolving power of an optical instrument. Certainly, to do that, we want to make sure that the angular separation is much larger than the theta. So in terms of the design of the optical instrument, we want to make sure that the minimum separation, governed by the formula theta equal to lambda over A, you want theta to be as small as possible. If theta need to be as small as possible, you want your lambda to be small and you want your A to be large. So what does that mean for the optical instruments? Let's take a look at A first. If A needs to be large, what it means for the optical instrument is that you will like the telescope, you will like the aperture of the optical instrument, like a telescope, to be as big as possible, to be as wide as possible. And the width of the aperture of a telescope will also be wide. So that's the reason why you use really huge telescope for you to study stars. They are very far away, in order for you to be able to resolve the different stars. Next we want to ensure that lambda is as small as possible. If you want lambda to be small, you want the frequency of the light used in the optical instrument to be as high as possible, since C is equal to F lambda, and C is 3 times 10 to the power 8 meter per second. So which means that C is a constant. So if frequency of the light source is very high, then your wavelength is very small. In turn, it will ensure that the angle theta, which is the minimum angular separation, is as small as possible.